All right, today we are talking about electricity. In the previous chapter, we were talking about creating charges, focusing primarily on the relative concentration of electrons that were present on a material or an object, where if our object had an excess of electrons, which are negatively charged, then we said that that particular object or material was overall negatively charged. If our material was lacking in electrons, then kind of by default, it would be labeled as positively charged because it would have fewer negatives than positives. In this chapter, we are now focusing on those electrons that are now moving. So rather than being static electric charge, where we were concentrating on the buildup of charges on a material, now we are going to focus on the actual movement of those electrons, or what happens, why the electrons move, how they move, and we refer to that as electricity. So the first thing we're going to discuss is this vocabulary word current. Current is the rate of flow of the electrical charges. So when we are talking about electricity, again, our root word here is focusing on the electron. So we are dealing with moving electrons. So these moving, or what we sometimes refer to as flowing electrons, are going to create this particular current. We measure current in amperes, that is the formal name for it. We most commonly refer to it as amps, and we will note it with a capital A or some abbreviated version of amps or amperes. You can see from this illustration that I have an electric circuit here, and my charges are moving around the circuit. So it says here that electricity is a flow of electrons around a circuit. And then I made a little note, aka current would be another name for that flow of electrons. Our unit for current is amps, but what exactly is an amp? Well, an ampere or an amp is a ratio of coulombs per second. So it says here that we can calculate our rate of electron flow, or what we are going to call our current, by taking the electrical charge measured in coulombs, so that would be our variable Q, and dividing it by the amount of time in seconds. So if we had some sort of timer or stopwatch here, where it was measuring for us how many seconds it took for these electrons to pass by, we would say what was the electrical charge, how much electric charge passed this particular location, and how many seconds or fractions of a second did it take for those charges to pass by. So that rate of phrase, remember, means that we are timing something, we are dividing by time. So current is the rate of electrical flow, so it's how much time it takes for that electrical charge to pass by. We have a couple of example problems here for calculating current. The first question says, how much current is flowing through a light bulb when it takes 24 seconds for 18 coulombs of charge to pass through its filaments? So we are going to identify our variables here. Our time is 24 seconds. My charge, that is a typo, but we're going to go with it. 18 coulombs is a really big charge, but that's okay. And it says that they want to know how much current, so I is what I am solving for. So my formula is I is equal to Q over T. So for this question, we are simply going to divide 18 by 24. And that gives us 0.75. And our unit here would be amps. And so I'm just going to choose to write that with a capital A. So 0.75 amps of current for this question. The second question says, a motor draws 2.5 amps. How many coulombs of charge pass through it in 15 minutes? Remember that I would like for you to make sure that you are listing out your givens for all of these questions. We will come across our units provided in, or I'm sorry, our variables provided in different units from time to time. So if the unit given is not the standard unit that we need for the mathematical relationship being expressed by our formula, we got to make sure that we go and convert that, okay? So here, my current was given to me as 2.5 amps, and they gave me a time, but they gave it to me in minutes. So I have to make sure that I go and I convert that to seconds, okay? So when I convert from minutes to seconds, this gives me 900 seconds. They are asking how many coulombs of charge. That is the unit for my variable Q. So I equals Q over T. If we are solving for Q, then we are going to say Q is equal to I times T. So my charge is going to be 2.5 times 900, because I want that in seconds. And that is going to give 2250, which, according to the question, we need 2 sig figs. So we're going to say that our charge is, we can either express this as 2300 coulombs, or if you wanted to write that in scientific notation, that would be 2.3 times 10 to the 2. All right, so now let's talk about something called electrical potential energy. Work must be done on a charge in order to give it its energy. Remember, we learned work and energy and the concept of work being performed, and that is then transferred into energy in a previous chapter. So we're going to take that same concept and we're going to apply it here. There must be work done on a charge in order for it to acquire some amount of energy. So the work that is done on the charge is equal to that charge's potential energy. And remember, what the charge is that we are referring to are our electrons, okay? So work is going to be performed on the charge. Now that charge has potential energy as a result of the work. If there is a difference in the potential energy, that is going to cause those charges to then move, and they're going to move so that they go from low potential energy to high potential energy. So we are actually going to be using the word voltage to refer to this potential energy difference moving forward. Okay, so voltage is a vocabulary word. It's going to be one of our variables. It will be a capital V in our formula, and it's also going to be a capital V for our units. So the potential energy difference is called voltage, and this is what is responsible for causing our electric charges or our electrons to move. Voltage is potential energy per charge. So voltage is a value that represents a ratio that tells us how much energy is available per coulomb of charge. We are going to measure it in what we refer to as volts, but a volt would be joules per coulomb, okay? How much energy per coulomb of charge. Batteries are one example of a voltage source. So a voltage source in general is going to be whatever is responsible for providing that potential difference that's going to give those electrons a reason to move. So a battery, a single battery is referred to often as a dry cell, but this is just one of the types of voltage sources that we could have that would cause our electrons to move, but it is the one that we're going to focus on in this chapter, okay? A battery is a device that uses chemical energy to convert that into electrical energy, which is what is going to cause those electrons to move. So it says here the charges that flow out of the battery carry energy to the electric devices. So our charge, remember, these are referring to our electrons, and it's technically not one single electron. This is a bundle of electrons that we refer to collectively as a coulomb of charge, okay, a bundle of electrons. So in this little illustration, we can see what looks like, I guess, men carrying beakers that are full of something on a portion of the picture, and then those beakers are empty on another part of the picture. So let's just take a quick look at this and see what this is trying to illustrate to us. So let's say that these little men represent our coulombs of charge. Okay, these are our charges. So they are going to exit the battery carrying energy. They are going to take that energy and move it along the wire, give that energy to the electric device. So the energy is going to be used by the light bulb in order to give us the light. So that electrical energy in this particular case will be converted into light energy. So you can see after they have exited the light bulb, they are out of energy. They have given their energy away. We did not lose our electrons. The electrons are still there. Remember, electrons are actually already present in the wire, okay? It's simply the electrical potential difference or the voltage source that gives those electrons a reason to move. It gives, you can imagine it actually taking those electrons and pushing it out of the battery, forcing it to move forward through the wire. The wire is full of electrons, so it's kind of a line effect. The whole line moves together. Okay, so all of these electrons are moving around that circuit, and they are simply transferring energy. In this case, they gave all of their energy to this light bulb so that they return back without energy. And so now they are going to go back into the battery. Again, the battery is providing energy to these electrons so that they can then continue through the circuit or continue to follow that line and fuel that light bulb with more energy. All right, so our battery is taking the chemical energy stored inside of it, converting it into electric energy, which is what is allowing those electrons to feed that light bulb so that we can then get light energy from it. And these electrons that are here coming out of the battery are pushing the electrons in front of it forward, so these guys don't just stop once they get to the light bulb. That line continues to move, and so they're going to end up going back to the battery and then recharge, for lack of a better word here. They're going to recharge through the battery. They're going to regain that voltage. Okay, so again, voltage is a ratio that tells us how much energy is available per coulomb of charge. So we have areas in our circuit, and actually terminals, poles, whichever word you prefer to use, on our voltage source that has different electric charges or different amounts of potential energy. So depending on what that electrical potential energy is, that will determine whether this is the end that the electrons are fueling from, where they are exiting, or is this the end that the electrons are returning to so that they can get more voltage from that voltage source. So it says here on this last bullet, one terminal has an excess of electrons. So if we recall from the previous chapter, that means that we would refer to that area as being negatively charged because of its excess of negatively charged electrons. And one terminal or one end of our voltage source will have a lack of electrons, and so we label that as a positive. So we have a difference here in our voltage, and so that is going to identify the ends that our electrons are going to come out of the battery and return back into the battery. So we're talking about these electrons moving around, and there was an illustration there that had a direction. Those electrons were being pushed forward out of the battery and were coming back into the battery. So we actually talk about these moving electrons, not just current, meaning, hey, the electrons are moving around, and they don't just move around randomly. They actually have a direction that they move. So let's cover a couple of vocabulary words here. We have direct current and alternating current. Direct current is often referred to as DC. Alternating current is AC. So DC says that the electrons are going to move through that circuit or through that system following in one particular direction. So in this previous illustration, the direction Let's see, if we think of this as being kind of a circular oval shape that we're looking at, we can say that this is clockwise, okay? So here I have my electrons moving in this direction, going around the circuit, right? So the direction is the same for the entire illustration. At no point did these electrons decide that they wanted to turn around and march the other way. They were all marching in the same direction, moving quote unquote forward, or in this illustration, we could describe this as being clockwise. So having one direction is referred to as a DC current. Now, this is what we see when we have a voltage source like a battery, where we have a designated positive and a designated negative pole or terminal or area. Because remember, it's that interaction of those charges that causes the electrons to move. So when we talk about an alternating current, this does not have a set direction. Now, it's not random. There is still a method or a predictable direction, but it's not a situation where the electrons will always be traveling clockwise, okay? If we have an alternating current, where our positive and negative terminals, or where those positive and negative poles are, actually changes. And so those electrons are going to perhaps be moving clockwise in the original setup, but then if my electrons are moving clockwise and then the poles flip, well, because of the whole positive negative interaction, instead of my electrons moving clockwise, if the poles become reversed, well, the electrons are going to change their direction in response to that, and so now they're going to move counterclockwise. And so in the case of an alternating current source, the positives and negatives are constantly moving, and so the direction that those electrons are traveling, be it clockwise or counterclockwise or however we choose to describe that direction, it's going to switch back and forth. So that's why we call it alternating current. This is what we get when we plug something into an outlet in the wall. Those use alternating currents, okay? All right, so what direction does current flow? So how we describe the direction, how we determine whether that flow should be described as being clockwise or counterclockwise actually kind of depends on what we are analyzing here, okay? Now, we just finished our chapter where we were learning how positives and negative charged things interact with each other. We set the foundation that anything dealing with electric charges is because of moving electrons or rearranging loss or gain of electrons. Remember, we do not have positive charges moving around. The positives comes from the protons are in the nucleus. If we're changing or moving our protons, we are creating nuclear reactions, okay? And that is not what is happening here. So everything that we discuss with our electric charges is always the result of electrons that are moving. So I'm going to take a moment here and we're going to look at a little demonstration on our gizmo. So I have here a circuit and we can see that the light bulb is on. Okay, so this is very similar to the illustration that we were just looking at on the slides, and we can see that our electrons are moving, and right now I have the simulator showing us the direction or the current, and I have it set to show us the direction of the electron flow. So this is the actual physical direction that the electrons themselves are moving. But when scientists were first learning, understanding how charges work and electricity works and all the details that we now know so well, initially they didn't have any foundational knowledge. And so some of the information that scientists learned was actually misinterpreted up front. So in the case of electric circuits, we actually have learned, and what we typically discuss as common conversation is kind of like a general everyday knowledge, is the original thought, which actually illustrates for us how a positively charged thing would move. So we call this conventional flow. And if you notice, the direction of the electron flow compared to the direction of the conventional flow, they are actually backwards. They are opposites, because we now know that it's the electrons that are moving. And since electrons are negatively charged, and originally they thought that it was positive charges that were moving, it makes sense that the direction of the conventional flow is opposite from the direction of the electron flow, okay? So I don't want you to stress over what the electrons are doing compared to the conventional flow. I would like for you to understand that they are opposites. I would like for you to know that it is technically the electrons that are moving. But as far as what we are going to discuss moving forward, we are going to follow what you see right here on the simulator. This is conventional flow, and this is the hypothetical if we had positive charges that were moving around our circuit. Okay, so I have bolded it for you here. I want you to know conventional flow. And so conventional flow says that our electric current is going to flow from the positive or high voltage end of our voltage source to the negative or low voltage end of our voltage source. Okay, so when we start talking about our circuits in more detail in the future, that's the method. This is the thought process we're going to follow. All right, resistance. I came across this image just the other day, and I thought it was super cute and a very good illustration to represent the different variables that we have discussed so far. So we have our current, which is the little green guy, and remember this is the flow of those electric charges. We have our voltage, which is the reason that the electrons are moving in the first place. So we describe it as the quote-unquote push, and you can see in the animation or in the drawing, it's literally pushing the current through, which was so, I think, amusing to me. And then we have resistance, which is our last new vocabulary word here for this main set of vocabulary words that we need. So if we are looking at the illustration, we can see that the resistance, he sure is making it difficult for that poor little amp, that current, to flow through, right? And that's exactly what resistance is. Resistance is going to be measured in a unit called ohms, and I guess my Notability did not know how to process this symbol, so that is not the correct unit for ohm, or the correct symbol for ohm. An ohm is our unit for resistance, and it looks something kind of like that, okay? High resistance means slower current, so if our cowboy here is going to give more resistance, if he pulls tighter on that rope he has around that current, then it makes sense that it would slow down our little green guy even more as he attempts to make it through that wire, through that current. Down here it says devices that use electrical energy have resistance, so we will refer to our objects in our electric circuit sometimes as resistors. A light bulb is obviously a light bulb, but we may sometimes call it a resistor as we are describing or asking you to analyze what is happening. It says here the more devices we have, the more resistance. Each one of these devices is going to provide resistance, so if we pile on those devices, then we're piling on how much resistance these little currents are experiencing, okay? All right, so resistance is affected by three different factors. We have the length of our wire, we have the diameter or the circumference of the wire, and then we have the temperature of that system. So the longer the wire is, the more resistance the current will experience. The thicker, fatter, however you want to say it, the bigger the diameter here, the thicker the material is, the smaller that diameter will be. And so think about it, again, as this illustration here. The diameter is how much space this current has to move through. So as we tighten up this space, we are providing more resistance. We're making it more difficult for that current to flow. And then the temperature, higher temperatures are going to make it more challenging for the current to flow. So you need to make sure that you understand how these things affect the flow of our current. So if you'd like to, maybe you just pick one to remember. I would recommend remembering this one, and here's the reason why I'm going to recommend this. A coworker of mine said, think of Santa Claus. Santa is usually something that we think of as being a good thing, a happy thought, right? So Santa is short, thick, and he lives in the cold. It's a little corny, but I also thought it was kind of amusing, and I definitely think it will help to remember. So there you go for a little way to remember resistance. All right, so this brings us to Ohm's law. This is one of our main formulas for this chapter. This is the equation that we're going to be using the most in this particular chapter. So Ohm's law is the relationship between the voltage, the current, and the resistance. So the formula is V equals IR, where V is a capital V for voltage measured in volts. I is a capital I for current measured in amps, and then we have a capital R for resistance measured in ohms. So let's go ahead and work through a couple of practice problems here. It says for question number 1, how much current flows through a 10 ohm radio connected to a 12 volt battery? So I am being asked for my current, how much current. They give us a value of 10 ohms for my resistance, and drawing that ohm symbol sometimes takes some practice. Connected to a 12 volt battery. So my formula is V equals IR. In this question, they are asking us for I. So I am going to calculate my current by taking the voltage divided by the resistance. So 12 volts divided by 10 ohms is going to give me 1.2. And our unit here for current, remember, is amps. All right, next question. How much voltage is needed to run 3 amps through a 6 ohm resistor? So they are asking me for voltage, so I'm solving for V. I have I equals 3 amps, and I have R equals 6 ohms. And my equation, once again, is V equals IR. This time, no algebra needed. I am simply going to multiply 3 times 6, and that's going to give me 18. And we needed 2 sig figs here, so perfect. And my unit for voltage is volts, so 18 volts. All right, last question. A defibrillator sends 6 amps of current through the chest of a patient by applying 10,000 volts. What is the resistance of this path? So we have a current of 6 amps. We have a voltage of 10,000 volts, and they want to know what the resistance is. So my formula is V equals IR, and if we're solving for our resistance, then we divide both sides by current. So my resistance is going to be voltage divided by current. So I'm going to say 10,000 divided by 6, which gives me 1, and then it's a whole bunch of 6s. I'm going to go ahead and write this in scientific notation rather than writing it twice. So they gave us 3 sig figs in our current. This value here has no decimal, so it's technically only 1 sig fig. I'm going to go ahead and cheat a little bit, and I'm going to choose to write it as 2 sig figs. So this is going to be 1.7 times 10 to the 3rd ohms for my resistance. All right, the last thing that we need to talk about today is power. So power is a ratio, once again. It's how much energy is being used in a second. So if you recall, we've actually also already learned about power. We've learned about energy and we've learned about power in a previous chapter. And so we still are using the idea that power is watts, and it is still a ratio of joules per second. But when we are talking about electrical power, we describe electrical power as being voltage times current. So my formula here is P is equal to IV, where power is measured in watts. It says here in gray that a watt is joules of energy per second. So if we do the algebra, I just want to show you real quick that it is indeed still a watt. It still works out the same. We have current, which is going to be amps, times voltage, which is volts. And if you recall from the notes earlier, we said that current is the ratio of coulombs per second, and we said that voltage is the ratio of joules per coulomb. So when we substitute those in or expand our units, as I've stated in the past, then when we look at this multiplication problem, what we see is that we have coulombs in the numerator and the denominator, so they are going to cancel each other out. So I'm left with joules in the numerator, seconds in the denominator. Joules per second is what we originally learned a watt to represent. Okay, so you guys are going to be using P equals IV to calculate our power, but it still does represent a watt. And then we have a couple of practice problems here just to wrap things up. It says an air conditioner uses 2,160 watts of power as a current of 9 amps passes through it. What is the voltage used to run the air conditioner? So I'm going to take a moment and list out my givens for us. We have power. We have current. And they are asking us for the voltage. So P equals IV, where if I'm solving for voltage, I'm going to divide both sides by my current. So voltage is power divided by current. So I'm going to take 2,160 divided by 9, which gives me 240. And we do indeed need 2 sig figs for this calculation, so that works out perfect. We are solving for voltage, so this is going to be 240 volts is my value for voltage. All right, the next question, what is the power produced by a hairdryer with 9 ohms of resistance connected to a 110 volt outlet? In this question, they give us a resistance of 9 ohms. They give us voltage as 110 volts, and they are asking me for my power. So you may have noticed already that we do not have enough information to fit into the power formula that we were given. We said P is equal to I times V, but I do not know what my current is. So I'm going to need to go and figure out what that current is. Now we can do this one of 2 ways. We can make it a 2-step problem. We can use V equals IR and take this formula and figure out what my current would be by rewriting that. We can perform this calculation over here and get a value and then plug it in, which is probably what most students would choose to do. The other option would be to take my power formula and then just simply say P is equal to V over R times V. Yes, that would give you V squared over R, whichever you prefer. I'm going to go ahead and work through this as a 2-step problem, just because that is probably what most of you would do, but both will work. And depending on what kind of information you have to work with, you may have to do the substitution of one formula into another if needed. So just wanted to point that out to you as an option. So when I perform my calculation over here to find my current, I have 110 divided by 9. And that's going to give me 12.2 repeating as my current. So then I'm going to take that. Oh, hey, guy. I don't need you to do that. Thank you. I'm going to take that value, that's what I was trying to do, and I'm going to substitute it in over here so that I can perform my power calculation. So 1.2, if you're doing this as a two-step problem, be sure to use that answer button so you get all of those repeating decimals, times my voltage of 110, which is going to give me 1,344.4, and those fours just keep on going. So power is equal to 1,000